Force on a current carrying conductor. Consider the case of a current carrying conductor placed in a magnetic field through which current I is flowing in the direction as shown in the figure. Consider L as the length of the conductor as shown in the figure. It experiences a force upwards because it is kept in a magnetic induction field of strength B. Now, the magnitude of the force experienced by this current carrying wire is given by dF is equal to dq into V cross B, where B is the velocity with which the current is flowing, B is the strength of the magnetic field. Now, dF can be written as dq. In place of V, write dl by dt cross B. In the next step, dt is brought under dq. It is written as dq by dt dl cross B, or dF is equal to I dl cross B, because dq by dt is nothing but current. Or from dF, if we want F, we can write this as I L cross B. Now this is a vector force. Length in a particular direction we will take, so it is a vector. B is strength of the magnetic field, it is a vector. This force F experienced is perpendicular to both L and B. Since it is a cross product, the magnitude of force is given by F is equal to I B L sin theta. Now, if theta is 90, that is B and L are perpendicular to each other, then the conductor will experience maximum force given by I into B into L, because sin 90 is 1. Now, since force is a vector quantity, the direction of this force is given by Fleming's left-hand rule. And what is that rule? When you stretch the 3 fingers of your left hand perpendicular to each other, the central finger will say is pointing in the direction of current. The forefinger or index finger in the direction of B. Then the thumb will point in the direction of the force. So direction of force is given by Fleming's left-hand rule. Now, let us consider what is force between 2 parallel conductors. So this is a conductor, another conductor of length L placed parallel to it. Now, the current in the first conductor is I1, current in the second conductor is I2. Distance between the 2 conductors is D. Now, this conductor will have its own magnetic field. This conductor will experience its own magnetic field. The first conductor will experience a force due to the second conductor's magnetic field. Similarly, the second conductor will experience a force due to the magnetic field of the first conductor, because they are kept in the magnetic field of each other. They are close by, they are not far apart. Now, if we call the first conductor A and the second conductor B, the magnetic induction of A is mu0 by 4 pi 2I1 by D, or force experienced by it is I2 BA into L. FB is force experienced by B. You have to write BA here because it is kept in the magnetic field of the first conductor. Force experienced by the second conductor is current flowing through the second conductor, I2, into magnetic induction of the first conductor into length. In place of BA, substitute this. Then bring this L to the denominator, cancel 2 and 4, you will get FB by L equal mu 0 by 4 pi 2 I1 I2 by D, or F